Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, let's get started on lecture 2. So all of the heavy lifting in week 2 occurs during the first 2 lectures. We covered a lot of ground in lecture 1. We'll cover more in lecture 2 and get familiar with the results that we derived in the first lecture. And then the pace will slow down a little bit. Okay, so let's jump into this. These are the expressions that we've developed. And hopefully now, when you look at these, they don't just look like a set of complicated expressions. They really make sense. You know, then we're ready to proceed. So these are our basic coupled electrical equations for the electric field we measure and the heat current that we measure. There's also a heat current due to the lattice that we're not going to be talking about until lecture 5 or so. And then the 4 parameters in these first 2 equations, we have simple expressions that relate them to the properties of the material. And what I want to do now is just go step by step through those 4 parameters. Well, through the electrical conductivity. The Seebeck and Peltier coefficients are basically the same. They're simply related by this fundamental relation, the Kelvin relation. We'll talk about the thermal conductivity, and then we'll talk about trade-offs and relationships between these various parameters. Okay, so we want to develop a feel for these parameters. Let's look at the conductivity, and let me first of all think about a lightly doped semiconductor, non-degenerate. Fermi level is well below the bottom of the conduction band or well above the top of the valence band. So we can approximate our Fermi function then in those cases by an exponential. So the probability that states in the conduction band are occupied is very low. Just to make things simple, I'll approximate the energy-dependent mean free path by a constant. You know, think of it as the average mean free path at different energies. And we'll assume a bulk 3-dimensional material in which the number of channels varies linearly with energy as we go into the band. Okay. Now, we can simply work out this integral expression and compute the electrical conductivity. If you've had some semiconductor courses before, you're probably used to writing the electrical conductivity as NQ-mu. This is really not a fundamental way to write electrical conductivity. The way to write electrical conductivity is up here in the first line. If you confront a new material, you shouldn't try to figure out what's the mobility, what's N. You should compute the electrical conductivity from these fundamental expressions. Then if you want the mobility, you simply equate this expression to the fundamental expression. That tells us what the mobility is. So if we do that, we can express N in terms of the distance between the Fermi level and the conduction band. This is just traditional semiconductor physics. The constants out front are known as the effective density of states and depend on the effective mass. And when we do this mapping, we find that the mobility is something with the units of velocity that ends up being a well-defined thermal velocity, about 10 to the 7th centimeters per second for typical semiconductors. Thermal velocity times mean free path divided by 2 kT over Q. Now, there's an Einstein relation that says that D over mu is equal to kT over Q. And that applies because we're near equilibrium. So if we take kT over Q times the mobility, we get an expression for the diffusion coefficient. And this is a nice, simple, easy to remember expression. Diffusion coefficient is thermal velocity times mean free path divided by 2. Thermal velocity is centimeters per second. Mean free path is in centimeters. So the units are centimeters squared per second, just what they should be for a diffusion coefficient. Okay. Now, this may look a little different to you. You may be used to writing mobility as Q tau over M, or tau is the average time between scattering events. This is the same thing. It's just that we're expressing mobility in terms of the average distance between scattering events instead of the average time between scattering events. Okay, so the conductivity is something that we're familiar with. What about a metal or a heavily doped semiconductor? You know, in this case, my Fermi energy is way inside the band. If I look deep inside the band, all of the action is concentrated very close to the Fermi level, and I can think of this Fermi window as just a delta function centered right at the Fermi energy. That's where all of the action is. Then I get a very simple expression for the conductivity. It's quantum of conductance times the mean free path at the Fermi energy times the number of channels at the Fermi energy. So it's a nice, simple, easy expression. The mathematics is simple. Notice that the conductivity is not proportional to the number of electrons in the conduction band, because only the ones that are near the Fermi energy, inside the Fermi window, those are the only ones that matter. But the number of electrons in the conduction band determines where the Fermi energy is, and where the Fermi energy is determines how many channels there are. So the conductivity is indirectly related to the number of electrons, even though most of the electrons are not carrying current, only the ones in the Fermi window. Now, in the general case, we can evaluate this expression, and we can rewrite it in a very physically suggestive way. The conductance, the conductivity, is 2q squared over h, the fundamental quantum of conductance, times average mean free path times number of channels. So fundamental constants. In this case, it's the average number of channels inside the Fermi window. Those are the only ones that contribute to current flow. And then it's the appropriate average mean free path of those electrons in the Fermi window. So we get a very simple expression. And we know that if we measure the conductivity, that one of the things that makes semiconductors so useful is that we can vary the resistivity or the conductivity over many orders of magnitude, 6 or 7. We do that by doping the semiconductor and changing the Fermi level and moving it from way below to way above the bottom of the conduction band, or way above the top of the valence band to way below the top of the valence band. So semiconductor doping allows us to vary that Fermi level dramatically. Now, knowing where the Fermi energy is going to be very important for us in thermodynamic calculations, thermoelectric calculations. The way we find the Fermi level is that usually we know the electron concentration, and then we ask what Fermi level produces that electron concentration. So we have to integrate the density of states times the Fermi function. In general, when we do that, we end up with a Fermi-Dirac integral. The order depends on the particular shape of the conduction band. If you're not familiar with Fermi-Dirac integrals and you want a refresher, I refer you to these set of notes that you can find on the web. And what you find is that if your Fermi level is way below the bottom of the conduction band, then the Fermi-Dirac integral reduces to an exponential, and we get our non-degenerate expressions. If it's way above, we get a medal. If it's in between, we have to deal with Fermi-Dirac integrals. And unfortunately, for thermoelectric calculations, we're frequently in between. So you'll see many thermoelectric coefficients expressed in terms of Fermi-Dirac integrals. So it's worth getting familiar with Fermi-Dirac integrals. So once we know the doping, we know where the Fermi level is. The doping determines the Fermi level. The carrier, if we know the carrier concentration, we can deduce what the Fermi level is. And the location of the Fermi level determines the conductivity, also determines the Seebeck coefficient and the other thermoelectric coefficients. So it's very important for us to deduce where the Fermi level is in an experimental situation. Okay. Now let's turn our attention to the Seebeck coefficient. You'll remember that when we derived our expression for the Seebeck coefficient, we took the energy that has to be absorbed from the thermal lattice in order for an electron to hop from the contact up into the channel at energy E. We weighted it by the conductivity of that channel, and then we normalized it by integrating over all of the channels. That's the Seebeck coefficient. If the states are above the Fermi energy, we have a negative sign. If they're below, we get a positive sign. So the Seebeck coefficient is very simply related to the average energy at which current flows with respect to the Fermi level in the contact. And if I divide by K, Boltzmann's constant, and multiply by it, I can express this average energy of current flow with respect to the Fermi level in dimensionless units of kT. The parameters out front then are 86 microvolts per Kelvin. That gives me a sense as to the magnitude of the Seebeck coefficient. And then depending on where the Fermi level is, which depends on the doping of the semiconductor, I can deduce what the magnitude of the Seebeck coefficient is. Here's some measured data. And if you look at this measured data, this is for N and P-type germanium. You can see the magnitude of the measured Seebeck coefficient. 0 means that the Fermi level is located either at the bottom of the conduction band or at the top of the valence band. If all of the energy flowed right at the bottom of the band, we would get this dashed line. But the current actually flows a little bit above the bottom of the band, so the Seebeck coefficient is a little bit bigger because the average energy at which current flows is a little bit above. And in fact, if we have a non-degenerate semiconductor, the current flows about 2 kT above the bottom of the conduction band, depending on some details of scattering, which is why the red line is slightly above what you would deduce if you thought the current flowed right at the bottom of the conduction band. If you become very degenerate, then all of the current flows at the Fermi level, which is way up inside the band. In that case, the average energy of current flow is the Fermi energy. And in that case, the Seebeck coefficient approaches 0. There is no difference between the average energy of current flow and the Fermi energy. And that's why the Seebeck coefficient of a metal or a very heavily doped semiconductor is very small. Lightly doped semiconductor, it's very large because there's a big difference. Heavily doped semiconductor, it's very small. Now, these are some numerical calculations for a variety of different materials. The conduction and valence bands of germanium, the conduction and valence bands of gallium arsenide, the conduction valence bands of bismuth telluride, the conduction band, I guess, of graphene. So you can see that all materials basically have very similar Seebeck coefficients versus Fermi energy. It's mainly controlled by where the bottom of the band is with respect to your Fermi level. There are some details that come in depending on the exact shape of the band and the details of scattering, but they aren't large deviations. The Seebeck coefficient is basically determined by the band edge and by the location of the Fermi energy. Okay, so we've discussed conductivity, we've discussed Seebeck coefficient. Since the Seebeck coefficient is related to the Peltier coefficient by the Kelvin relation, we've also discussed the Peltier coefficient. Now let's have a look at the electronic thermal conductivity and see if we can understand that a little bit as well. Okay, so there is a fundamental relation, as we've discussed, between the Seebeck coefficient and the Peltier coefficient. That's why I've only discussed one of the two. I don't need to discuss both. Now, there is also a relation that we would expect between the electrical conductivity, 1 over the resistivity, and the electronic thermal conductivity. Since electrons are carrying heat and they're carrying charge, heat flow and charge flow should be intimately related. Now, there is a relation, but it turns out it's not as fundamental as the Kelvin relation. But we expect the higher the electrical conductivity, the higher the thermal conductivity. Okay, so let's look at our expressions for the electronic thermal conductivity. We had this relation for the short circuit thermal conductivity. We can translate it into the open circuit thermal conductivity. The open circuit thermal conductivity is the one that we will use most often in applications. So that's the one that we're most interested in. Okay. Now, if you look at the one that we can most easily calculate, what it is not the average energy of current flow with respect to the Fermi energy, but the average value of the square of that conductivity times the electrical conductivity. If you look at the Seebeck coefficient, that was related to the average energy of electronic flow. So if we put these two together and determine the electronic thermal conductivity under open circuit conditions, what we'll find is this rather complicated looking expression. Now, what's inside the curly brackets frequently doesn't change too much for common semiconductors. So we can write this as temperature times electrical conductivity times something that we'll call, or that people call, the Lorentz number. It's the evaluation of all of these. So then it looks simple, but we've hidden a lot of complicated things inside that Lorentz number, which involves integrals of various quantities over what might be complicated band structures. But if you want to carry something around in your head, you know, people rely on these simple estimates widely, even though they're not always true. But for a non-degenerate semiconductor, three-dimensional semiconductor with parabolic bands, This Lorentz number is 2 times Boltzmann's constant divided by Q quantity squared. If you're a completely fully degenerate parabolic band semiconductor in 3D, then the numerical factor is pi squared over 3. So it only varies between about 2 and 3. Now, if you have an unusual band structure, you can get different numbers. But under most common situations, people will ask themselves, are we non-degenerate or are we degenerate? They'll use the appropriate Lorentz number, the measured conductivity, and that's the way that we can get a handle on the electronic thermal conductivity. Okay. Now, just to remind you, we have the measured voltage difference or electric field. We have the measured heat current, which also includes a part due to phonons or lattice vibrations that we haven't discussed yet, but we will in the future. So these are our basic equations, and we're getting familiar with the parameters in the electrical part of those equations. Okay. Okay. Now, we'll just point out that the lattice also carries heat, and it's something that we're just going to mention now and discuss more later. What you'll find is that both of them carry heat, but in metals, it's the electrons that carry most of the heat because we have a lot of electrons, a lot of electrical conductivity. In semiconductors, even in very heavily doped semiconductors, it's the lattice that carries most of the heat. So it's really important for us to understand both of those parameters. So just to recap, we have a simple expression for the electrical conductivity. We have a simple expression for the Peltier coefficient. We can easily get, for the Seebeck coefficient, then we can easily get the Peltier coefficient. And if we write the electronic thermal conductivity in terms of the electrical conductivity, in terms of this Wiedemann-Franz law and Lorentz numbers, then we have a simple way to get a handle on it as well. If we encounter a material with an unusual band structure, then we have to go back and make sure that we have the correct numerical factor, which might be quite different. And then we have the lattice thermal conductivity that we shouldn't forget about. Okay, now I just want to run through, in the end, a quick estimate of how would we estimate these parameters for a real material. Let's say N-type germanium. So we'd like to estimate these 4 parameters in our 2 coupled current equations. Let's assume a lightly doped sample at room temperature with a typical mobility of 3,200 centimeters squared per volt second. We can assume non-degenerate semiconductor statistics, fully ionized dopants. We'll put in typical numbers of effective masses and effective densities of states, so we can plug some numbers in and see what we get. Okay. Now, if you're curious about what the mean free path is in a typical semiconductor, we can easily estimate that this way. The diffusion coefficient we get from the mobility. It's just by the Einstein relation, it's just kT over Q times mobility. We know the mobility, so we can deduce the Seebeck, the diffusion coefficient, as 83 centimeters squared per second. We can deduce the thermal velocity because it's related to the conductivity effective mass. It's about 1.55 times 10 to the 7th centimeters per second. The diffusion coefficient is simply related to the thermal velocity times the mean free path divided by 2. We solve this equation for the mean free path, and we find that for this particular sample, the mean free path is just a little over 100 nanometers at room temperature. That's a relatively long mean free path. Okay, so now let's go through these parameters easily, quickly, beginning with the resistivity. We know the doping. If the dopants are fully ionized, we know the concentration of electrons in the conduction band. We know the mobility. It's presumably been measured. So we simply multiply N times Q times mu. We get the electrical conductivity. We take 1 over that, and we get the resistivity. For this particular sample, it's 2 ohm centimeters. Okay, let's look at the Seebeck coefficient. So we'll use our same material parameters. We'll remember that the Seebeck coefficient is related to the location of the Fermi energy. If we know the electron concentration, 10 to the 15th per cubic centimeter, if we know the effective density of states from the effective mass, we simply solve that equation for the location of the Fermi energy in units of kT. Then, if we assume that the current flows 2 kT above the bottom of the conduction band, then the average energy of current flow is the conduction band bottom plus 2 kT. Plug numbers in, and we'll get minus, it's negative because it's N-type, minus 970 millivolts per degree Kelvin. So if we have a 1 degree Kelvin difference across this resistor, we'll measure almost 1,000 microvolts or 1 millivolt. Okay, let's look at the Peltier coefficient. This one is easy. Just multiply the Seebeck coefficient times temperature, and we'll end up with minus 0.3 volts for the Peltier coefficient. And finally, let's estimate the electronic thermal conductivity. So if we look at that, we'll use the Wiedemann-Franz law, and if we can deduce the appropriate Lorentz number, then we can estimate the electronic thermal conductivity. It's a non-degenerate semiconductor. The Lorentz number varies between 2 for a non-degenerate and pi squared over 3 for a degenerate. So we'll use 2. We know the electrical conductivity. It's 1 over the 2 ohm centimeter resistivity that we deduced. So we plug numbers in, and we get an electronic thermal conductivity of 2.2 times 10 to the minus 4 watts per meter Kelvin. That's a pretty small number, actually. Okay. So all of these parameters depend on the location of the Fermi energy. It's a useful exercise to do this with a differently doped sample. But we should also realize that heat flow depends both on the electrons carrying heat and on the lattice carrying heat. If you look at the measured thermal conductivity due to the lattice for germanium, it's 58 watts per meter Kelvin, much bigger than 2 times 10 to the minus 4 due to the electrons. So most of the heat in this sample is carried by the lattice. Very little of it is carried by the electrons. Okay, so we could summarize here to say that the basic equations that we have are these 2 coupled current equations. We've discussed the 4 parameters due to the electrons in some detail. We've mentioned that there is this parameter due to the lattice that we're going to discuss at more length in Lecture 5. But hopefully by now you've got a physical feel for what the magnitude of these numbers are, the physics of where they come from, the mathematics of how you relate them to detailed band structure when you need to do those calculations. And if you're given a sample and need to estimate those 4 parameters, we went through an example to show you how you can easily do that. It would be a good exercise for you to test your understanding. Assume the germanium is doped 10 to the 19th and run through the same set of calculations and see what the parameters are like in that case. That'll give you a good feel for how they vary with doping density. Okay, so we've done the heavy lifting in lectures 1 and 2. The pace will slow down a bit for the rest of the course. And we'll start to look in more detail about how we build devices, what determines the performance of the devices, the various trade-offs involved, some of the novel structures that we might use in order to enhance performance. So I'll look forward to talking with you again when we do Lecture 3.